not so bad. We'll continue with 3 presentations for the afternoon, and then we will have a panel discussion. And that will be the end of the day after that. So keep awake, please. Take some coffee. And we will start with Greg from MedService. If it's all good, you got your slide. Very nice. It's all yours, Greg.
Hi, thanks, Phil. Hi, everybody. I just want to talk a little bit about the impact of machine learning on weather models. What's happening here? It's an important concept for MedService. Thank you. And to talk about it, I'm just going to talk a little bit initially about weather models themselves. So it all pretty much started by a paper in 1904 by Wilhelm Bjerknes, and he suggested that the atmosphere itself is a dynamical system, and it's governed by a set of equations. And if you know the atmosphere at a particular state, and if you could integrate those equations forward in time, you could get a forecast. And here are the equations that he was talking about. Essentially, it might look a bit mathy, but the first 3 of them are just trying to describe how the velocity field of the atmosphere is changing. And if you're changing the velocity of something according to Isaac Newton, you should be applying a force. So on the right-hand side, we've just got a bunch of forces there: pressure gradient term, Coriolis, curvature term, and friction, and so on. And then we've got a thermodynamic equation, how the temperature is changing, and also a mass continuity equation down the bottom there. So it's pretty simple, and these are simple physical principles. That's all I'm trying to get across in that slide. So how do we do it? Well, what we do is we, first of all, discretize the globe, and then somehow we come up with an analysis. So we may use satellite data, surface-based observations, and so on, and we come up with analysis of the state of the atmosphere. And then we integrate those equations that I showed before forward in time. And that's essentially the guts of a numerical weather prediction model. Of course, there are other little bits and pieces. We have to sort of figure out what's going on sub-grid scale, and also things like the incoming solar radiation, things like that. But in a nutshell, that's essentially how these models are run. And we've been doing that since the 1950s. There's a photo there of the ENIAC computer, which was used in 1950. It was part of the Manhattan Project at one point. Anyway, the improvements over the last 70 years have effectively been from subgrid scale physics improvements, satellite data, launch satellites, better data assimilation methods, and finer resolution due to increased computer capacity. We do use machine learning, and up until now, I guess it's been more or less an adjunct to the weather forecasting process. So we might improve time series. So up on the left there, I've got a time series of air temperature at Auckland Airport, and we apply machine learning techniques to improve that. We might downscale from a coarse resolution model to a high resolution model, which we do at MedService as well. And we might look at methods for trying to figure out what the next in a sequence of radar images might be. Excuse me. But what's happened lately is that we've got these successive snapshots of the state of the atmosphere, and we can actually train machine learning models on that alone. We can actually forget about the physics. Those equations I showed at the start, just park them over here for a moment and just use machine learning models to generate what the next state of the atmosphere will be. And it begs the question, so are the physical equations no longer needed? Are we still seeing any benefit from the physical models? And this was all, I guess, a bit of a curiosity up until, this year, basically. So 5 years ago, I think the skill of these machine learning models was about the same as a 200-kilometre resolution global model. But now they're actually competing with the global models. And this has come about primarily through agencies such as Google and Huawei and NVIDIA that have made huge progress over the last year. In particular, Huawei's Pangu Weather, it now has the same skill as the European Centres model. And the European Centres model is pretty much thought of as the preeminent model, global weather model in the world. So this is having a profound impact on, where should we be spending our money on these weather models. And I've noted there that EC have actually opened up their verification scheme to Huawei, and they actually put the forecasts on their website as well. This is a paper by the architects of Pangu Weather, so the people working for Huawei, and they submitted it to Nature in July this year. So it's pretty recent, and it's having a bit of a global impact. So there's some fundamental benefits that machine learning models bring, and once you've trained them, they can take seconds to apply. So if we've got a state of the atmosphere there, then instead of waiting for, 2 hours, 3 hours for a physical model to run, we can get the answer almost instantaneously. And this has a huge impact on the on weather forecasting. You can imagine an extreme event unfolding, and the forecaster will get the new information hours earlier than they otherwise would. Another benefit is that we can run ensembles cheaply. We can perturb that state of the atmosphere slightly all around the globe and apply the same machine learning model to that and get a whole raft of solutions. And this gives us some information about the distribution of weather solutions as opposed to one deterministic model. We do this now, but what we do is we tend to back off the resolution to make it cheaper. But now we don't have to do that. There are challenges. It's not all fantastic, but I guess a couple of the challenges are if we're using skills such as root mean square error to train these machine learning models, then they may not be handling extreme events very well. And this is a graphic I took off the European Centres website, and it's to do with Tropical Cyclone Freddy. If you recall, in March this year, the tropical cyclone formed northwest of Australia, then went all the way across the Indian Ocean and made landfall at Madagascar, I think it was. And anyway, up the top three of the panel there are all based around physical models. So the analysis, what the EC Centre is predicting at 48 hours, and the ERA5 reanalysis, they all use physical models in some sense. The two bottom ones are machine learning models. So Huawei's Pangu Weather and NVIDIA's ForecastNet. And you can see that Pangu Weather's pretty much got the position right, but it's both Pangu Weather and ForecastNet have really backed away from the correct intensity. And this is likely to be using skill scores such as RMSE during the training phase of the machine learning model, backing away from very intense systems. Another challenge that we're definitely going to face at Met Service, if these become sort of the bread and butter of forecasting the weather, is that currently what happens is the forecasters will follow one or more models, and then what they will do is they will mine those models for diagnostic information. They will try to get things like model drive soundings and things like that to figure out how intense thunderstorm activity is going to be, how far east across the divide is the rainfall going to spread, and so on and so forth. If we have a machine learning model, then all the data in that grid there may not be physically consistent. the pressure field may not line up with the velocity field and so on. So we won't be able to do this data mining. And that's a bit of a concern for us. But of course, there are solutions to these things. One possibility for the extreme events is that we use generative models. And one way around this idea that we need to have our models being explainable is to somehow enforce the physical constraints. If you like, enforce those equations back onto the solutions that the machine learning model uses, either by introducing a physical layer or something. So, in summary, what we've got is that machine learning models are now as skillful as physical weather models. And if people had said, if you asked somebody 10 years ago in the weather forecasting game whether that would be likely, they would have laughed at you, I think. But now we're right at the point where this is a reality. Physical models I think there's always going to be a role for them, particularly in coming up with the analyses. They do some things that are nicely objective, that I guess may be critical. As I've mentioned, explainability is an issue. I can sort of see a sort of a revolution happening in the forecast space here. And the global centres are starting to commit resources to this. I'm not sure how this is going to sort of play out. I know ECMWF, they've got a small team of data scientists, and I think about 3 people or so far. But this year they launched a massive online learning experience, which was called the ECMWF MOOC, MOOC. I recommend you guys have a look at that if you haven't already. But I think what will happen is probably partnerships will form between these global numerical weather prediction centres and agencies like Google and NVIDIA and so on. Okay, thanks. That's about all I've got.
Yeah. Thank you. 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 Sorry, looks like it doesn't work. Any question for Greg? Yes, Bernard.
Investigate that is kind of everything that we can say that is due to physical models and and actually conditions you might trust one or the other, like neither of the happens. Maybe you just need to pay the specialist model something.
Yes.
You would have a text that says you also have an input.
Yep.
This is how you do that.
Yeah, I suspect that the physical models might be superior in the first few hours. Say they're running on physical principles, perhaps. But I think the longer the forecast horizon goes, it's hard to look past some of the machine learning models, I think. And the fact that they give you this information a lot earlier, is just, we have to notice that and say, okay, where to from here?
Absolutely improvements there is another problem. The flood prediction is the same issue.
Yeah.
The river size that for a long time has been learned quite easily.
Yeah, yes, that's right. Yeah. I mean, unfortunately in weather forecasting, the extreme events are the important events, and as we've seen lately, and so it'll be interesting to see how the machine learning models are sort of embraced by the forecasting community. But yeah.
Thank you. Yes, Eb.
In this paper that they published today, already say something about the physics-based layers in the network or the potential for those. I mean, it seems like an obvious way to try to merge the power of the physics-based models and how to deal with that work.
Yeah, I haven't read the paper fully yet. I know ECMWF have been talking about introducing physical layers, if you like, but it's one of these things that what is the role of the forecaster if we don't have that explainability? And it's kind of an important one because if a forecaster is talking to a regional council about the progression of a severe weather event, then they have to actually understand the physical processes that are going on. Otherwise, what's the point, I guess?
Sorry.
Did you consider the wow.
Yes, you could. I mean, I don't think there's a lot of difference between that and just applying a machine learning over the top of the current run of the numerical model, the physical model. I think the big thing is that if you did that, though, you would lose that time advantage. If you had to wait for the latest run of the physical model, perhaps.
Yeah, sorry. So keep your question actually for break. After we will have to keep running.